So in this little lecture here, I want to talk about how we actually go about getting thermodynamic data and use this in analyzing a system. So when we're talking about thermodynamic data, I'm talking about U and H. Because when we're dealing with the chemical, we need to know its internal energy and its enthalpy and what they may change from one state to another when we're doing analysis on work or heat. So generally there are two ways we can get thermodynamic data about a chemical or a material. First one is tabulated data. So if you look in the back of your book, you will see what are known as the steam tables. And we're definitely going to go over these in more detail, but the steam tables generally list at a given temperature and pressure, it will list U and H for that material, in this case steam or water. So in the back of the book you have, if I look up a given temperature and a given pressure, say 1 bar and 25 degrees Celsius, in the back of the book it will tell me what the internal energy and the enthalpy are at that given state. So that's one way that we do it, is to just use tabulated data. And the other one is through formulas. Now the formulas often do not tell us what the actual internal energy is at a given state, but they tell us the changes in internal energy or enthalpy from one state to another. And one of the most common ones that we're going to deal with a lot is that one I'll just talk about in just a second. So one of the most common formulas we'll use is the heat capacity formula. And the heat capacity formula tells us how the internal energy or the enthalpy of a system changes by going from one temperature to another. So in this case, we're going from temperature 1 to temperature 2. And that may be an increase in temperature. We may be heating up by going from temperature 1 to 2, or we may be decreasing in temperature. Maybe we're going from a hot temperature at T1 to a low temperature at T2. It doesn't really matter, the equations are the same. So the formula for the change in internal energy, or the difference between the internal energy at state 2 and state 1, is just defined as delta U, and that's this integral right here. So we are going to need to know a little bit of calculus to work with some of these formulas when it comes to changes in internal energy and enthalpy. But it's not anything difficult, it's just straight old integration. So if you're a little rusty on your integration from calculus, you may want to brush this up. And so this formula for the change in internal energy is just the integral from T1 or T2 to T1, and it's the function CV times dt. And this right here, CV right here, this is a formula that tells us that once we plug it in, when we integrate it, we can use to calculate the change in internal energy. And so oftentimes CV is a function of the temperature. And we'll talk more later on about this, but if you look in the back of your book, there are different formulas for CV values or CP values in the back of the book. So you can take those functions that are functions in temperature, plug them into this formula right here, and integrate it to get the change in temperature from state T2 and T1 here. We have a similar formula here for a change in enthalpy, except it involves this value CP. And so if we have the formula CP, we can plug in here and then integrate it to go ahead and get the change in enthalpy. Now you're saying, okay, what's the difference between CV? CV is the constant volume heat capacity. So this is the change in energy related to constant volume, which is usually just associated with delta U. So whenever we're doing a delta U, we're going to deal with CV. CP is constant pressure heat capacity. So whenever we're dealing with a system that is constant pressure, we're going to have you deal with CP. The other thing to also remember is that delta U, or involving CV, involves systems that are closed. So if we have a closed system, we'll deal with CV. If we have an open system that's flowing, we'll deal with this formula down here, or CP. And so there we have a common way that we'll deal with changes in energy by using these formulas. And we'll definitely go through examples and homework problems in class. So another form of energy transfer or energy change that we're often going to deal with is latent heat. And latent heat is the energy associated with a phase change. So whenever we have a material change phase, whether that's from a liquid to a solid, solid to a liquid, liquid to a gas, etc., that is a latent heat change. And two latent heat changes, or two different types of latent heat that I mentioned here, is the heat of vaporization and the heat of fusion. Heat of vaporization is simply the energy required to vaporize or boil a liquid. So you put some water on a pot and you start heating it up. Well, there is a certain amount of energy required to boil that water, and that's the heat of vaporization. Heat of fusion is the energy required to melt a solid. So if I take some ice and I set it out, I'm going to have to add some heat to that ice to melt it, and that's the heat of fusion. So opposite of vaporization is condensation. So if I take a gas and I condense it into a liquid, that's the heat of condensation. And the heat of vaporization is the negative of the heat of condensation. So the energy it takes energy required to take a liquid to heat it up to a gas phase, evaporate to the gas phase, is the opposite in energy that it takes to take the material from the gas phase to the liquid phase. So if you know one, you know the other. You just put a negative sign on it, change the sign on it. So the opposite of the heat of fusion is the heat of freezing. Heat of fusion, again, is just the energy it takes to take to take a solid and melt it to a liquid. Heat of freezing is the opposite, where we take a liquid and we cool it down to form a solid, just like freezing ice, making ice cubes and so forth. And again, this is the negative of the heat of fusion. And all of these values we can look up. So if I look up, for instance, water at 1 atmosphere, and in the back of the book, we should be able to find out what the heat of vaporization is. This right here is the heat of vaporization for water. I looked it up in the back of the book, and it's 40.66 kilojoules per mole. So if I have 1 mole of water and I want to boil it, it requires 40.66 kilojoules. Notice that this is a delta H, so this is a change in energy, change in enthalpy, the amount of heat I have to put in. Oftentimes we'll write H for the change in enthalpy or the change in heat. It's also vaporization, but there's this line up here across that, and whenever we have a property that's on a per mole basis, or it depends on the amount of material, we'll often put bars on top to specify that, because that lets us know it's per amount of material. And so this is, again, just an example from water. We can look up other materials for the heat of vaporization, condensation, fusion, or freezing. But whenever we have a phase change, we have to take into account the latent heat through these various different values here. So I want to set up the equations that are useful for a closed system when you're doing an energy balance. So here I have a system where we have some material in a box. And this could be water, it could be air, it could be whatever, it doesn't really matter. Within this box it's closed, so we have no transfer of the material in and out of the box, so nothing's going across the barrier, it's fixed within the box. But we can have energy transfer into the box, either through heat or work. So if heat is just the transfer due to a temperature gradient, so if the temperature outside is higher than the temperature in the box, heat will transfer into the system. If the temperature outside is lower, heat will transfer from inside the box to outside. We can also have work if this is a deformable shape. So if this box can change shape, so we had this example with a piston earlier, we can compress it, for instance, by applying work. And so that's energy it would take to compress this box. So if I write out the the energy balance equation, this is the energy balance equation right there. Delta U is equal to Q plus W. So delta U is just simply the change of the internal energy of the material in the box. How does it change? By adding in heat or work. So the only real way we can go ahead and change this is by either adding in heat or somehow changing it through work by changing the shape of the box. And we use the convention here that positive, negative. So the convention here is that if we are putting heat into the system, meaning that the temperature outside is larger than inside, we're having heat go from the hot to the cold, then the heat is positive. So Q is a positive value. Same thing if the heat temperature outside is lower, meaning that heat is transferred from inside the box to outside, then Q is negative. Got to remember these conventions, because if you don't get these conventions right, you're going to mess the problem, make a lot of mistakes on the problems. On work, if we are putting work into the system, meaning we're compressing it, we're squishing this box size down, then work is positive. On the other hand, if the box is performing work on the surroundings, meaning that the box is expanding, then work is negative because the box is performing work on the surroundings. So again, keep these sign conventions in mind. So this equation, delta U is equal to Q plus W, it's the basis for analyzing the energy changes of a closed system. And if I tell you what the Q is for a given system, and assuming there's no work, you can calculate the change in internal energy of the material in the box. And as a reminder, oftentimes when we're dealing with delta U, we may get U values from the tables in the back of the book. We may get U values from the equations on integrating heat capacity. We may get them from various sources. So here's just written out what delta U is, where U2 is the internal energy at state 2 at some time, and U1 is the internal energy at state 1 at some other time. And so we might calculate these again using data or formulas. So let's just go through the energy balances for an open system. In an open system, we have some material flowing in and out. So we have flow rates and in and out. If this is a steady state, the amount of moles amount of material going in is equal to the amount going out. And we have here the full equation for the energy balance here. So the change in enthalpy, which is the change in energy of the material as it's moving along, plus the change in kinetic energy. If this fluid changes its speed, then we'll have a change in kinetic energy, plus the change in potential energy. If this has a change in elevation, there's a change in potential energy, and that's equal to the amount of heat we put in. The amount of heat we put in plus the amount of work we put in. And again, the same sign convention applies. If we're putting in work or heat, these are positive values. If we're removing heat or we're having the system do work on the surroundings, work is negative. And these have dots here. Dots because these are work or heat per time. It's an energy per time is the units, because this is a flowing system. So everything is per time. So we just got to remember this when we're dealing with open systems. These are per time. If we just assume that the kinetic energy and the potential energy are negligible, which is the case for most of the applications we're going to deal with, then it turns out that the equation for the energy balance on a flowing system, an open system, is just delta H is equal to Q dot plus W dot, or any heat or work terms. And again, delta H is the change in enthalpy of this fluid as it's moving through the system. Let me just summarize these right here. The equations, here I have the change in internal energy for a system, U2 minus U1. It's the difference in internal energy from a given temperature and pressure, and a different temperature and pressure, or state 2 and state 1, is equal to delta U. It can be oftentimes written as N, the number of moles, times the delta U, which is a specific quantity, meaning this is the change in internal energy per mole. So if I multiply energy divided by mole times number of moles, this will be in units of energy, and that's equal to Q plus W. H2 minus H1, this is the change in enthalpy for a system, and that can be oftentimes written as N dot, which is the flow rate of the material, times the delta H bar, and the delta H bar is the enthalpy per mole, and that's equal to Q dot plus W dot.